Okay, welcome to the tutorial for this first part of eigenvectors and eigenvalues and eigenvectors chapter. Okay, so we are in point 10. This is going to be the example. As I have said in the previous video, we have studied the theory, the definitions of some important concepts, and also you have seen some lemmas. We have also seen a theorem and a corollary. So in this tutorial, we are going to apply all those concepts we have learned so far. And this tutorial is going to be a bit long because I would like to apply all those different concepts, okay? And also we are going to see some concepts from the previous chapters. So let me give you the question for the following matrix T, which is equal to 2, 0, 0, 3, 2, 0, minus 3, minus 3, and 1. Okay, find. Let me go to next. Okay, let me do this. Let me split the page into two. Find. Okay. Part 1. The characteristic polynomial. And we all know what we mean by characteristic polynomial from the previous video. Characteristic polynomial. Okay, part 2. Find the eigenvalues. Okay, the associated eigenvectors, and okay, let me do this. The eigenvalues, okay, to make things a bit clear, to be the associated eigenvectors, and part C, the associated eigenspaces. Okay, we have seen all these concepts, the characteristic polynomial, eigenvalue, eigenvectors, eigenspace. We have defined them in the previous video. Part 3 of this tutorial, we will be asked to find 3a, the algebraic multiplicity, and b, the geometric multiplicity, and part 4 of the tutorial is will be asked to find a basis. A basis associated with the the eigenvalues. Okay, so this is going to be our tutorial. We are going to answer those 4 questions. Okay, so let me start here. Part 1, we are asked to find the characteristic polynomial of t. Let me put of t. The characteristic of t. And we have seen in the previous video that the characteristic polynomial is basically the determinant of t minus xi. Okay, and here let me explain to you where does the determinant, or where does this expression come, where does it come from, t minus xi. In the previous video, we have seen the definition. Okay, I didn't go into depth about where we got determinant of t minus xi from. In the previous video, we have defined what we mean by the eigenvalue or eigenvalues and the eigenvectors of a transformation. Okay, if you recall, we say that a transformation, okay, has a scalar eigenvalue lambda if there is a non-zero vector zeta such that the transformation t zeta is equal to lambda zeta. Sorry about my zetas. Zeta. This is the transformation definition. Basically, in matrix form, what does it mean is we have a T, which is the big T, which is the matrix representation of T, okay, in a basis. T multiplied by zeta. Instead of zeta, let me work with beta, okay? Because we will, in the question, okay, we mostly use beta. T, okay, no, let me stay with zeta so that I don't confuse people. T zeta equals to lambda zeta. Okay, so here what I'm going to do is to bring lambda zeta to the right hand side. So we have T zeta minus lambda zeta, which is equal to 0. Okay, so I'm going to factorize T. Okay, they have zeta in common equals to 0. Minus lambda, I can't just write minus lambda because lambda is a scalar. Okay, so I can't take a scalar from a matrix. So I'm going to turn the lambda into a matrix. So I'm going to write lambda I. Okay, so we have the definition of eigenvalue and eigenvector is what we have here. T minus lambda I multiplied by zeta, the eigenvector, is equal to 0. So basically, a transformation T has an eigenvalue lambda, okay? If we have T minus lambda I all multiplied by the eigenvector zeta equals to 0. So, as you have seen in the previous chapter about the determinant, we use determinant to see if the matrix is singular or non-singular. So we have a such equation T minus lambda I multiplied by zeta equals to 0. We want to see if it is singular or non-singular. And we have seen that if we have a non-singular, then the determinant t minus lambda I should be different from 0. Okay, but singular means we have t minus lambda I equals to 0. That means singular means we have a unique solution and here equals to 0 means we have no solution or many solution, infinitely many solutions. So we have no solution or infinitely many solutions. So as you can see, when we have such equation, okay, t minus lambda I multiplied by zeta equals to 0, to be able to have infinitely many solutions for this equation, what do we need to have? We need to have the determinant t minus lambda I equals to 0. Okay, so actually that's where the expression characteristic polynomial t equals to determinant of t minus xi is coming from. Okay, in the definition we use x instead of lambda. As you can see, it's more convenient to use x instead of lambda in our calculations. But here is the origin of that expression about the characteristic polynomial. As you have seen, in the previous chapter, the characteristic equation is when we let the determinant t minus xi equals to 0, so that we can see the values for which of lambda for which the equation has infinitely many solutions. Is that okay? I know in the books, most of the time we just write the characteristic polynomial t minus xi, but we don't explain where does it come from. But because we assume that you have done all the previous chapters, the chapters about determinants and the chapters about the linear systems, and where why we say determinant of t minus xi should be equal to 0, okay, to have the characteristic equation. Is that okay? So all of this is just extra. You don't need it for our tutorial. You don't need it. It's just extra to explain it to you. So this is extra, not needed. Okay, you don't need to be able to do the rest of the question. So let's continue. Next page. Okay, so remember here we are dealing with the characteristic polynomial. Okay, and we say that is determinant t minus xi. So recall our t is equal to 200 320 minus 3 minus 3 1, and xi is going to be equal to x0 0 0 x 0 0 0 x. I'm sure you understand why. Okay, the identity matrix, so we multiply x by the identity matrix. So now the determinant t minus xi is going to be equal to determinant of 2 minus x 0 0 3 2 minus x 0 Okay, and minus 3 minus 3, 1 minus x. Okay. Okay. So we need to find the determinant. If you remember from the previous chapter about determinant, how do we find the determinant of a matrix? We have two options. The first one is to use Gauss method, and the second one is to use Laplace expansion formula. In questions about eigenvectors and eigenvalues, it's more suitable to use Laplace formula. Okay, so recall. So let's find the determinant using Laplace formula. So recall Laplace expansion formula or cofactors expansion formula. But let me just write Laplace formula. Laplace formula says if we have a transformation or matrix T, then determinant of, let me write A so that you don't get confused. Determinant of A is equal to the sum of J, which is, J is the number of columns, going from 1 to n minus 1 to the power of I plus J, A, I, J, let me write small a, which are the entries of A, okay? Small a, I, J, multiplied by the determinant of the minor of A tilde, I, J. And I'm sure you remember how to get the minor, okay? Matrix Aij is the matrix we get if we delete the A row and the J column of the big matrix A. Okay. So let's do the expansion along row 1. Okay, so we are working with this matrix. Okay, expansion along row 1. So what do we have? Determinant of t minus xi, okay, is going to be equal to, okay, we are going to do the expansion. So, okay, let me write it more. So we have minus 1, 1 plus 1. Okay, we are working with, we are expanding along row 1. This is 1, row 1. So, multiply by 2 minus x, the determinant of the minor 1 by deleting row 1 and column 1 is 2 minus x minus 3 is 0, 1 minus x. Plus minus 1, 1 plus 2. The second entry is 3 multiplied by determinant of deleting row 1 and column 2. We have 0, 0, minus 3, 1 minus x, plus minus 1, 1 plus 3, minus 3, determinant of 0, 0, 2 minus x, 0. Okay, I'm sure you know how to get a determinant. If you don't recall, go back to our previous chapter and I have plenty of tutorials for that. Okay, so here we have 2 minus x multiplied by how to find the determinant of a 2 by 2 matrix, you know, okay? 2 minus x multiplied by 1 minus x. And here we have minus 3 multiplied by 0. And here as well we have minus 3 multiplied by 0. Okay, when it comes to determinants, I'm going to fly through them because you should know how to get the determinant. 2 minus x to be squared multiplied by 1 minus x. So this is our polynomial, characteristic polynomial, determinant of t minus xi. Okay, let me make the box in green. So this is our characteristic polynomial. let me here do, okay, we are asked part 2 to find the eigenvalues. So part 2, if you remember, let's recall the question we asked. Part 2a, we are asked to find the eigenvalues. Let me do it here. 2, part A, eigenvalues. How do we find the eigenvalues? To find the eigenvalues, we just solve the characteristic equation. Solve the characteristic equation. And if you recall, the characteristic equation is t minus xi equals to 0. We have just found t minus determinant of t minus xi. So characteristic equation is determinant of t minus xi equals to 0. So t minus determinant of t minus xi equals to 0 means we have a 2 minus x squared multiplied by 1 minus x equals 0. That means we have 2 minus x equals to 0, or 1 minus x equals to 0. That means we have x equals to 2 or x equals to 1. And these are our eigenvalues. Let me change. So our eigenvalue, lambda 1 is 2, and lambda 2 is 1. I know I should say probably lambda 1 is 1, lambda 2 is 2. It doesn't matter, okay? Let me write it this way. Okay, so this is the end of the this part. Let me write. Okay, in part B, we are asked to find the associated, let's go back to our question, associated eigenvectors. Okay, let me do it next page, part 2b. We are asked to find the associated eigenvectors. How do we solve the associated how do we find the associated eigenvectors? If we remember, I said the definition we have given for eigenvectors and eigenvalues can be summarized as the following equation. Okay? If you don't remember the definition, go back to the previous chapter. So basically, we have the following equation: t minus xi multiplied by our zeta equals to 0. Instead of zeta here, let me change it with beta, okay? T minus xi, or we can just say t minus xi multiplied by beta equals to 0. That means a transformation represented by the matrix big T has an eigenvalue, have eigenvalues x and eigenvectors beta if we have the following equation. Okay, so in order to find, we have just found our eigenvalues, the x's, which are the lambdas. Now let's find the eigenvectors b's. How do we find the associated eigenvectors? As I said, we need to solve this equation. So basically, to be able to find okay, so let me rewrite this equation. We have t minus xi, and previously we have seen that this is 2 minus x 0 0 3 2 minus x 0 minus 3 minus 3 1 minus x. Okay, I'm just rewriting the equation, this equation. Okay, just rewriting it. Multiply by beta. Okay, b1, b2, b3 equals to 0, 0, 0, 0. So to be able to find the eigenvalues, okay, we need to solve this equation, but instead of x's, let's use lambdas. Okay, so let me change to find the associated eigenvectors, solve the following equation. Okay, I'm just going to repeat the previous equation, but using lambdas. Okay, so we need to solve the equation 2 minus lambda 0, 0, 3, 2 minus x minus lambda, not x, 0, minus 3, 1 minus x, multiply by b, b1, b2, b3 equals to 0. Okay, so how do we solve such a linear equation? We are very lucky because our matrix G is already in echelon form. Otherwise, we need to, reduce it to echelon form. So let me do. So we have this. We have we have two values for betas. Okay, lambdas. So for lambda 1, if you remember lambda 1, we have two eigenvalues. Lambda 1 is 2, lambda 2 is 1. I know I should say probably lambda 1 is 1, lambda 2 is 2, but hey, it doesn't matter. Lambda 1 equals to 2. The equation becomes 2 minus 2 is 0, so you have 0, 0, 0. 3, 2 minus 2 is 0, 0. And minus 3, 2 minus 1 minus 2 is equal to minus 1. Okay, so we have b1, b2, b3 equals to 0, 0, 0. Okay, okay, so we have here 3 times b1, b2 minus 3 times b3 equals to 0. And for the second row, we have minus 3 b3 equals to 0. And for the third row, we have minus. Okay, let me go to next. Okay, yeah, so that I can write all of them together. So here we have 3b2 minus 3b3 equals to 0. And minus 3b3 equals to 0, and minus b3 equals to 0. So this means we have b3 equals to 0. We have here we have 3 for the row 1, 3b2 minus 3b3 equals to 0 means 3b2 is equal to 3b2 is equal to 3b3. That means we have b2 equals to b3, which is equal to 0. b2 equals to 0. So to be able to write the solution for this equation, we have b1 b2, b3 equals to b1. Okay, we don't know it. b2 is 0, b3 is 0. So this is equal to 1, 0, 0, b1, such that okay, so we can write it the solution like this. So let me go step by step. Okay, we have been asked to find the associated eigenvectors. So the eigenvector associated with the lambda 1 equals to 2 is the following. So the associated eigenvector eigenvectors is the following: 1, 0, 0, b1, with b1 being different from 0. As you remember, we cannot have a trivial eigenvector. Okay, so that's the eigenvectors associated with the lambda 1 equals to 2. And I'm not sure if I will have enough space, but let me try it here on next page. Okay, yeah, so for lambda equals to, we have two values for lambda, 2 and 1. For lambda equals to 1, our equation becomes, okay, if you remember, we are solving the following equation: 2 minus, okay, this one. We are solving this equation. Okay, 2 minus lambda. Okay, so I'm not sure if you would like me to rewrite the equation we are solving, but yeah, let me rewrite it here. So we are solving this equation. Okay, 2 minus lambda 0, 0, 3, 2 minus lambda, this is lambda 0, minus 3, minus 3, 1 minus x, sorry, minus lambda, multiplied by b1, b2, b3 equals to 0, 0, 0. So here for lambda equals to 1, we have the following matrix: 2 minus 1 is 1, 0, 0, 3, 1, 0, and minus 3, minus 3, and 1 minus 1 is 0. Okay, b1, b2, b3. Okay, let me give you a quick note here. If you remember, when we were doing the characteristic polynomial, I said we have two ways of finding the determinant of a matrix. We can use Gauss method or Laplace formula. Here you have noticed that I use Laplace formula. It's just for revision purposes, but I can go for a shorter way by using Gauss's method. And yeah, I remember you know how to find determinant, because this matrix is already in echelon form. So to be able to find its determinant is very easy using Gauss's method. We just multiply down the diagonals. Okay, we don't need to do all of this, but I did this just for you know, to help you recall. Most of the time we don't have we are not lucky to have the metrics to be in echelon form, so we have to do when it comes to dealing with eigenvectors and eigenvalues, is better to use Laplace's formula. Okay, so let's continue our question. So let's solve right now this linear system. We have b1. Okay, b1 plus 3, b2 minus 3, b3 equals to 0. We have b2 minus 3, b3 equals to 0. And here, of course, we have 0 equals to 0. So let us solve this. Let me, okay, maybe I can split this page into 3. This means we have b2, which is equal to a third of b3. Okay, we can parameterize the solutions. So writing the leading variables in terms of the free variables, and from our previous chapters, you know how we can write down the solution sets of linear systems by parameterization. And when it comes to row 1, we have b1, which is equal to minus 3 b2 plus 3 b3. Okay, which is equal to minus 3. We said that b2 is a third of b3 plus 3 times b3, which is equal to minus b3 plus 2 b3, which is equal to, sorry, plus 3 b3, which is equal to 2 b3. So b1. Now let's write this. So we have the following. No, it's not a third, it's 3. Why did I write third here? Sorry about that. Sorry. This is not a third. Okay, b2 is equal to 3, b3, and b1 is equal to, okay, minus 3 plus minus 3 b2 plus 3 b3, and so we have minus 3 here, 3 b3 here, and 3. Okay, so we have minus 9 b3 plus 3 b3, which is equal to minus 6 b3. That's b1. We have b2. So the solution set of it, the linear system, is b1, b2, b3, which is equal to, we said that b1 is equal to minus 6 b3, b2 is equal to 3 b3, and b3 is just b3. So which is equal to minus 6, 3, and 1 b3. So now let's write down the associated eigenvectors is written as follows. So we have b1. Let me write it in green as the previous one. Is equal to minus 6, minus 3, and 1 multiplied by b3, with b3 being different from 0. Okay, so that's the eigenvectors associated with the lambda 1. Okay, so let's go back to the questions. We have found the characteristic polynomial, we have found the eigenvalues, we have found the associated eigenvectors. Now we are asked to find the associated eigenspaces. Okay, very easy. Part C. Okay, part C. Associated eigenspaces. So how do we write it down? If you remember, for lambda 1, okay, so let me, I said for lambda, yeah, for lambda 1 is 2, lambda 2 is 1, so for lambda 1 equals to 2, We have the eigenvectors. How did we write the eigenvector, the associated eigenvectors? We have 1, 0, 0, 1, 0, 0, that's 0. That's 6. 1, 0, 0, beta 1 with beta 1 being different from 0. So the associated eigenspace, which is V lambda 1, so V2 is equal to all the eigenvectors. Okay, so we have 1, 0, 0, beta 1, such that beta 1 is belong to the complex numbers. Okay, so that's how we write down the associated eigenspace. Okay, maybe let me write it in green so that you can see it clearly. So the associated eigenspace is V2 equals to 1, 0, 0, that's 0, 1, 0, 0, B1, such that B1 is an element of C, complex numbers. Okay, and for lambda 2 equals to 1, we say that the eigenvectors are -6, 3, 1, B3, such that B3 is different from 0. Therefore, the associated eigenspace V1 equals to -6, 3, 1, B3, such that B3 is an element of C, of complex numbers. So this is going to be the end of question 2. Now let's go for question, part 3 of this tutorial. So we have found the eigenspaces. Now 3a, we are asked to find algebraic multiplicity and geometric multiplicity. Okay, so part 3a, we are asked to find the algebraic multiplicity. Recall from previous chapter, we said in the definition of about algebraic multiplicity, we say when a characteristic polynomial factors into something like x minus lambda 1 to the power of m1 multiplied by x minus lambda 2 to the power of m2, okay, up to x multiplied by lambda k to the power of mk, then the algebraic multiplicity, so if I can call it the am, let me call it the algebraic multiplicity is the algebraic multiplicity of lambda I is mi. Okay, so let me write it here, equals to mi. The algebraic multiplicity of lambda I is mi. So let's recall our characteristic polynomial, which is the terminal t minus xi. Recall, it factors into what? It factors into, okay, 2 minus x squared. It factors into 2 minus x minus 2. Do we have 2 minus x squared? Uh, 2 minus x squared multiplied by x minus 1, 1 minus x, multiplied by 1 minus x. So we can rewrite all of this into x minus lambda, but this doesn't matter. Okay, so that means the algebraic multiplicity when x is equal to 2 Okay, or if you want, we can rewrite this in let me rewrite it in x minus lambda. Here we have lambda minus x, but we can write it in as x minus lambda. Let me do this here. So let me take out minus from here. So 2 minus x can be written as a minus x minus 2. Okay, should be squared multiplied by, okay, I can also take minus from here, minus x minus 1. Okay, so I took out the minuses so that I can have them into x minus lambda. So here we have x, so this can be equal to x minus 2 should be squared multiplied by x minus 1, but I will bring that minus in front. So minus, so here we have it. As you can see, the polynomial is written in the form x minus lambda, and yeah, x minus lambda. So for lambda 1, okay, equals to 2, the algebraic multiplicity, okay, m1, okay, the power of x minus 2 is 2. The algebraic multiplicity is 2, And for lambda 2, which is equals to 1, then the algebraic multiplicity, I will call it m2, yeah, m2. So here is 2. m2 is equal to, the power here is 1. So maybe let me write it as full so that we don't get confused with all the subscripts. So the algebraic multiplicity is equal to the power of x minus 2, which is equal to 2. And for lambda 2 equals to 1, the algebraic multiplicity, okay, let me be a little bit lazy here, equals to 1. So that's how we find the algebraic multiplicity and yeah, the algebraic multiplicity of eigenvalues. So 3b, part B, we are asked to find the geometric multiplicity of the eigenvalues. And if you recall, it says that the geometric multiplicity is the dimension associated with the eigenvalue, okay? Of the the dimension associated with the eigenspaces of the eigenvalues. So yeah, recall that for lambda 1 equals to 2, the associated eigenspace, which is here, okay, lambda 1 equals to 2, the associated eigenspace, V2 is equal to 1, 0, 0, B1, such that B1 is an element of C. I check, yeah, B1 equals 2. So the dimension of V2, the dimension of V2 is equal to 1. So that's the algebraic multiplicity of associated with lambda 2. So for lambda, for lambda 1 equals to 2, for lambda 2, which is equal to 1, we say that the eigenspace is minus 6, 3, 1, minus 6, 3, 1, B3, such that B3 is an element of C. Okay, that means dimension of V1 equals to 1 as well. So let me give the summary here. For lambda 1 equals to 2, the geometric multiplicity equals to 1. And for lambda 2 equals to 1, the geometric metric multiplicity equals to also 1. Okay, maybe here as well. Let me write it out fully. The algebraic okay. So let me give you a quick note here. I didn't give it in the lecture. Note here is the geometric multiplicity of the eigenvalue must be less than or equal to the algebraic multiplicity. So in some questions you can see that geometric multiplicity can be equal to 2 or equal to 3, but note that the geometric multiplicity can never be greater than the algebraic multiplicity. Okay, and eigenvalue must have geometric multiplicity less than or equal to its algebraic multiplicity. So basically, the geometric multiplicity, if I can just write GM, should be less than or equal to AM. Okay, so good. Let's continue our questions. Okay, we have done part 3. Let's now do part 4. We are asked to find the basis associated with the eigenvalues. Part 4, basis associated with the eigenvalues. So if you remember from the previous video, okay, recall. Let me go recall. We have encountered the following theorem. Okay, the theorem says in the previous video, okay, says for any set of distant eigenvalues of a map or a matrix, a set of associated eigenvectors, one per eigenvalue is linearly independent. Donc, a set is that the set is linearly independent. Okay, so this is the theorem we have discussed in the previous video. So now, how are we going to find the the basis? Okay, so and recall as well, all of these I have written in blue is they are not important. Okay, it's just a recall. Okay, from chapter 2, the linear independence lemma. Okay, okay, let me do it later on, but let's find our basis. So basically, we have seen that if we have distinct eigenvalues of a map or a matrix, then if we take a vector from each associated eigenspace, then we can form a basis. Okay, so remember here, for when we have eigenvalues 1 equals to 2, we have the eigenspace v1 v2. Okay, because the eigenspace, if you remember from the previous video, is v lambda I, so that's why I wrote v2. The 2 is the value of the eigenvalue. Voilà. Okay, so v2 is equal to, the eigenspace v2 is equal to 1 0 0 b1, such that b1 is belongs to the complex numbers. And for eigenvalue, okay, so let me pick one vector from this eigenspace. So for b1 equals to 1, let me pick b1 equals to 1. I have my first vector, eigenvector. The first vector of my basis b1 equals to 1 0 0, as the theorem says. So if we have distinct eigenvalues and we pick one vector, anyone, okay, I can pick b1 equals to 5 or b1 equals to 10, but let me go for something very simple. b1 equals to 1, so I have a vector beta 1 equals to 1 0 0. Now for the second eigenvalue, for lambda 2 equals to 1, v1 equals to minus 6 3 1, b3, that's our eigenspace, such that b3 is complex number. Okay, just recall here. Here this is v2 1 0 0 b1, and v1 is minus 3 1, minus 6 3 1. Okay, so here as well, I'm going to pick for b3 equals to 1. I'm going to have my second vector of the basis b2 equals to minus 6 3 1. So according to this theorem, okay, according to this theorem, okay, we have our basis beta, our basis b equals to beta 1, beta 2, because the theorem says they are going to be linearly independent, and they are going to, so if they are linearly independent and they span our space, therefore, you know, they form a basis. So that means our basis B, and this is just one of the bases we can find. So basis B is 1, 0, 0, and minus 6, 3, 1. This is a theorem, so we are just going to believe it, but if you want, let me prove it, okay? Let's see if the theorem is right. Of course, the theorem is going to be right, but let's check just something. And this checking is also extra, is not needed. So anything extra I am doing, you don't need it to be able to answer the questions. It's just to explain things to you, okay? So let us check if the theorem is right. Theorem is right means let's see if these two vectors in the basis are really linearly independent. Let's see if they are really linearly independent, okay? So recall from chapter 2 when we did, vector spaces. So recall the lemma we have seen the linear independence lemma. Recall the lemma about linear independence. Okay, the lemma says the following. A subset S of a vector space, Okay, this is just extra, you don't need it, so you can just skip this, or you can just stop the video here, okay? Okay, this is just extra. So a subset S of a vector space is linearly independent if and only if and only if among its elements the only linear relationship C1 S1, so the S1 S2 are the vectors in the set S, and the C1s are the scalars, okay? Plus C2, the Cn's are the scalar, not C1. I mean C1, C2 are the scalars. C2, S2 plus Cn, Sn equals to 0, 0 vector is the trivial one. Yeah, in chapter 2 and chapter 3 we have worked a lot about how to prove that a set of vectors are linear independent or linear dependent, okay? So this is just a quick recall. It's the trivial one. That means C1 equals to C2 equals to Cn equals to 0, where Si is different from Sj. Okay, when I is different from j. So basically what we do is to take the linear combination of the vectors and see take the linear combination of the vectors, let them equal to 0, and see if the only time the relationship holds is when the scalars C1, C2, Cn's are 0. So the theorem here says that if we take a vector from each vector spaces, okay, and each eigenspaces, and we combine them, they are going to be linear independent. That's the theorem. So the theorem must be right. So let's check. Let's check if beta 1 and beta 2 are really linear independent. Are really linear. Let me just write it like that, linear independent. So what we are going to do, what the lemma says, it says that we need to take linear combination. So C1, B1, beta 1. Let's take C1, beta 1. So C1, beta 1 plus C2, beta 2 equals to 0. Let's see. For which value of C1 and C2 this relationship holds. So you have C1, beta 1 is 1, 0, 0, plus C2, beta 2 is minus 6, 3, 1 equals to 0, 0, 0. So here you have a C1 minus 3 minus 6 C2 minus 6 C2 equals to 0. We have 3 C2 equals to 0 and C2 equals to 0. That means C2 equals to 0 and C1, which is equal to 6 times C2 from row 1, okay, is equal to 6 times 0, which is equal to 0. So that means the only time the relationship C1, B1 plus C2, B2 holds is equals to 0 holds, that relationship holds, is when C1 equals to C2 and equals to 0. So that means, according to our linear independence lemma, the vectors, okay, beta 1 and beta 2 are really linearly independent, Therefore, yes, our theorem is right, because the theorem says if we pick a vector from each vector space, each eigenspaces, they are going to be linearly independent. Okay, thank you. I think this is the end of this tutorial. Is very long. Okay, so the tutorial was a summary about everything we have learned in this first part of our 5th chapter. Okay, we have learned about eigenvalues, eigenvectors, eigenspaces, characteristic polynomials, characteristic equations, algebraic multiplicity, geometric multiplicity, and how to find a basis, okay, associated with the eigenvalues. I think we can stop here. Thank you and see you in the next video.